You can get started, Jeremy.
Okay. Hi, everyone. Welcome to lecture 11. So this is the next lecture on generalization theory. And it's also kind of like the culmination of a lot of things that we talked about over the last few lectures. So yeah, let's get started. So I'm going to start out by like recapping a few of the points from last lecture about VC theory. Then we're going to talk about Bayesian data modeling, which is like one general approach to machine learning and data analysis. Then we're going to look at PAC-Bayes, which is basically an attempt to kind of convert these ideas into a generalization theory. Then I'm going to show you like 3 different ways of like working out this theory for neural networks. And then at the end, we're going to speak briefly about how this can be used to compare. You know, you've got 2 different neural network architectures, and you want to know which one's better without training them. Like, is there a way to do that? Okay, so let's start with the recap on last lecture. So we proved this VC generalization band, and what it says is that the probability that any classifier in our class of classifiers F, the probability that any of them get a substantially different train and test error is less than or equal to than this quantity, and the denominator depends on the number of data points. So as you ramp up m, the number of data points, this probability should get exponentially smaller, but only if this term doesn't grow exponentially. And this term measures the average number of different classifiers on a finite number of points, on 2m points. Okay, so I've just written out again like what was the basic mechanism of how this works, but the idea was that if you fix a single classifier, the probability that would get very different train and test error, yeah, like for that one classifier to get different train and test error, then from its point of view, like from the point of view of that classifier, something very imbalanced and unlikely happened during the data sampling. Like you don't expect to compute 2 empirical means and get very different numbers on each one. But if there are lots and lots of classifiers, then it can become actually quite likely that something unlikely happens to one of them. And that's the base. It's kind of like the difference between what's the probability of me winning the lottery or what's the probability of someone winning the lottery. Like one is unlikely, but the other becomes quite likely because a lot of people buy lottery tickets. So the advice from VC theory is sort of like, it's kind of like limit the number of people who can buy lottery tickets if you want to stop anyone from winning the lottery. But the way it measures the number of players in this analogy is the number of realizable dichotomies that the function class can realize on a finite sample. Anyway, that was just the recap. But does anyone remember what we thought some of the pitfalls were, or what was yeah, what weren't we happy about last time? So one of the things is it's probably too strong. Like, we don't care if some classifiers overfit. We just care if we only care about one classifier, and that's the one that our optimizer finds. So only care about the classifier found by our optimizer. Let's just say SGD for simplicity. Another thing, I think someone pointed out last lecture that it doesn't depend on the complexity of the training labels. It doesn't depend on the training labels at all. But you could imagine that there are some, like some labelings of our training data might be much harder to learn than others. But it's kind of blind to that. And that was the third drawback. Oh, and then there's just the main thing is that like neural nets can often realize all 2 to the m dichotomies and still generalize. So it seems like the VC theory stuff is very interesting, but it may not be it may just not be working in the right way for what we want in deep learning. But today we're going to talk about a kind of an alternative theory. But I guess kind of keep these drawbacks in mind because, yeah, my claim is that this other theory like resolves a lot of these problems. But yeah, just like keep these things in mind. So at this point, we're going to take a detour and talk about Bayes' theorem and like Bayesian data analysis and like what does any of that mean? Okay, so a Bayesian person will tell you that you only need one result for machine learning, sort of, but it's like this is like the most important thing. The idea is that you have a family of models and you have a prior over them, and you're not sure which one you want to use, but you're going to try and use the data to try and whittle down and pick one model. And the way that a Bayesian says to do this is, just you apply this theorem. So the probability that a particular model is the right one, given the data sample that you have access to, is equal. So we call this the posterior because you've used the data to change your distribution. So you've changed your prior into your posterior. And then the way that this happens is that you have a likelihood function which tells you, like given the model, how likely is that data to occur. And then the other term is called the evidence. And it's usually, maybe it's one that's sometimes glossed over because it's difficult to compute. It's just the normalizing factor of this distribution. But actually for us, it's going to be the most important thing. So we're going to like really go into detail on the evidence now. But before we do that, I guess one comment is that at least I've always been a little bit skeptical when someone told me that like Bayes' theorem is like the most important thing in machine learning, because it seems to be very different to what we do in deep learning. Because the Bayesian point of view is that the posterior distribution is the most important thing, meaning that you form a distribution over all models which are good given the data. Whereas in deep learning, you only deal with like point estimates. You randomly initialize the weights, and at the end of the training, you have a single model. You never form a posterior. You never even explicitly form a prior. So there's something like you should be a little skeptical because it just seems to be different to what happens in deep learning. But let's ignore that for the moment. So now we're going to dig into this term, the evidence, and we're going to try and unpack that. So right, the denominator of Bayes' theorem will be very important to us, and I rewrote the theorem here. So what does the evidence, this term P of data, what does that mean? It's like the probability of the data, but it doesn't mean like what's the probability of just like walking outside and someone hands you that data. It specifically means what's the probability that any model in our family kind of gives us that data. So it's the normalization constant. So it can be written as the probability of like summing over all models in our model family of the likelihood of the data given that given this particular model times the prior probability of that model. So this is the this is like sort of like the definition of what the evidence is. It's the you sometimes call it the marginal likelihood because you marginalize or you sum over all models in your model family. And I wanted the intuitive way that I think you should think about this quantity is that it's you can think of it as the probability of drawing a random model from the prior and finding that it fits the data. So I'm claiming that like this equation and this statement are really the same thing. So are there any questions at this point? Like, I
have a quick question actually. And you've kept this point unspecified, but the data is split into X and Y, right?
Yeah, like we're going to do that. So because we're going to be thinking about classification, the data sample is like X's and Y's. And yeah, so a model will be, what we're going to think of now is that each model is a weight vector for a classifier. And the class of all models is something like my neural architecture. And when we say the probability of the data given the model, well, actually, when we say the probability of the data, what you should think is what's the probability that I sample a random weight vector, I pass in my training inputs, and it reproduces my correct training labels. So that's what this means in the context of classification.
So I have a pedantic question. Maybe it's irrelevant for the lecture, and if so, we can move on.
Right.
Shouldn't this be given X? Given so X is sampled exogenously.
What does it? Sorry, what does exogenously mean?
It shouldn't be P of Y. So you have, and perhaps I'm being overly pedantic at this point, and if so, we can just move on.
Yeah, I think okay. What data means is that it's the events that I like. What this probability of data given model means is like what's the probability that that I pass my data. So I have a fixed data set at the beginning, data I already have, but what this event data means is that I pass the inputs that are in that data set through the model and it reproduces the outputs. But yeah, this is a very informal notation. So yeah, I think I'm going to try and clarify this a little bit more on the next slide, but
can you clarify again the difference between the architecture and the weights? So you kind of said like you pull out a model and it's a set of weights, but then you were saying the model is a set of all architectures. So wouldn't different architectures have different, I guess, is it like one architecture in different weights or like multiple architectures, all of which have different multiple combinations of different weights?
Yeah, not multiple architectures, just one architecture, which could be called models, and then multiple weight vectors for that one architecture.
Okay, thanks.
Yeah, let me try and clarify again, because okay, so now we're going to try and specialize this to like, what does any of this mean in the context of neural networks? So I've just copied and pasted the formula for the evidence, and in particular, right, we're going to be thinking of classifiers. So I'm going to simplify things by choosing a particularly convenient likelihood function. So remember, the likelihood function is this thing which we're writing as like probability of data given a model. But now by model, right, we really mean a particular weight vector for our neural architecture. And we're going to define this a convenient likelihood function, which is just 1 if model reproduces or fits the training labels. So the labels of the data exactly. And 0 otherwise. So the picture that you have in mind is that I have an architecture and it has a space of weights. So the weight space. And then there's like a kind of a subspace of solutions. And what a solution means is that solutions fit the training labels exactly. But anything which is not a solution means it makes at least one mistake on the training set. So we're sort of defining a solution to mean that probably this likelihood is equal to 1, and all of the non-solutions, the likelihood equals 0. So we can now plug this likelihood into this expression for the evidence, and it simplifies. And we find that you know, the evidence, the probability of the data given my network architecture, is equal to the sum. You know, we lose all of the terms from this sum where the model doesn't fit the data because these are 0. So it just ends up being the sum over all models, meaning all weight vectors that fit the labels exactly, the training labels exactly, of the prior probability of those weight vectors. So if you look at what this is summing the prior probability of weight vectors that fit the training data. So if you think about it, that's the total probability. That is the probability that I draw a weight vector from my prior on weight space, and I find that it fits the training data. Or geometrically, you can think of it as being it's like the volume of solution space, the volume of solutions divided by the volume of weight space. And this is the interpretation that I want to like take away for the rest of the lecture, or like we're going to use this repeatedly over the rest of the lecture. So I'll just like emphasize it again and then ask if there's any questions. But what this volume of solutions divided by volume of weight space means is it's like, what fraction of the entire weight space do the solutions occupy? And if they occupy the entire weight space, then this ratio is 1. And that says that the Bayesian evidence for my model class is also 1.
I have a question.
Yeah, go ahead.
Why we want them to like the model to fit labels exactly? I mean, in real world training, we never actually like achieve that.
That's a great question. So this is a simplification which I'm making because it's going to make everything easier to understand, but you can generalize all of this to the, you could define your solution space to be the class of models that get better than 95% accuracy, and everything goes through. But for simplicity, we're just considering a solution to be something that gets 100% accuracy, which is possible on some data sets.
Okay, thank you.
But like basically what I want is, does anyone have questions about this relationship between the evidence and this kind of geometric point of view?
I get the high level, what you've written down here. I'm a little confused, kind of like how this would look like if you were to write it down more formally. This this is kind of going off of what Ethan was saying earlier. Like, like how would this actually be written down if you have, like, let's say W is your weights and you have your X's and your Y's? Like, what would those equations look like?
Okay, good question. Let me try and do it.
I don't know if you have time right now to do that, but I think it would help me clarify a lot.
Okay, this would really be, you know, the integral over let me call my my integral over my weight space. Let me call weight space omega. The integral over omega of the prior probability of a particular weight vector times my likelihood function. But remember, my likelihood function is just, I've set it to be the indicator function of whether, you know, the neural network with weight vector W applied to input 1 equals the label 1, and then like analogous terms for all data points. So the indicator function that all of these conditions are matched for this weight vector times the element of volume for that weight vector. This is like the formal, right? And what I'm saying is that this is actually equal to, does this make sense? That this is just writing out the evidence as an integral rather than, like, here it's a sum because it's like informal and it's just like, you know, like freewheeling. But here it's like, it's actually an integral. I have some kind of prior measure on weight space, which could be Gaussian or something else. And then I have an indicator function which tells me, does the classifier implied by that weight vector fit the first data point? Does it fit the nth data point? And I have a volume element. And then I'm just saying that, you know, what this looks like, it just ends up being the volume of solutions divided by solution means something where this indicator function returns 1 divided by volume of weight space. Do you see why this integral ends up looking like this? Because, you know, if this indicator function wasn't there, we would just be integrating P of W over the whole space and we would get 1. But we're just, because we put this indicator function here, we're just picking out things that are solutions. So we only integrate the measure across over the solution space. Okay, I think at this point I have to keep going. But if you didn't connect this connection to Bayes' theorem, don't worry. The only thing you need for the rest of the lecture is that we're somehow interested in this quantity. Like, we have a weight space, we have a data set, and we're just interested in what's the volume of the solutions. Like how much of the weight space is occupied by solutions. By solutions meaning weight vectors that fit the training data. So this is all we're going to take away. Okay. I'm going to call that thing the evidence. The evidence is the number of solutions divided by the number of weight vectors, or the volume of solutions divided by the volume of weight vectors. And it really is the Bayesian evidence, but we can just think of it, define the evidence to be this ratio of volumes. It has some nice properties. So if you fix your architecture and you have two different data sets, one thing you might expect is that the easier data set would have more solutions and the harder data set would have fewer solutions, because, you know, maybe, yeah, I mean, that's just what my intuition would say, but obviously your intuition may disagree. But it seems to be potentially a way to measure the hardness of data sets based on like which data set has more neural network solutions for a given architecture. There's another point is that, and imagine now we fix a data set, and we have two different architectures, and one architecture for this data set has way more solutions, meaning a larger volume of weight space actually fits that data, for that architecture, a larger volume of the weight space fits that data set. Whereas for this other architecture, only a much smaller volume fits that data set. Then we might be tempted to say that this looks like a better architecture for the problem because, you know, somehow it's a better prior, or it's more inclined to fit that data. So it looks like the evidence can both tell us something about how good an architecture is and how hard a data set is. There's another, so this slide is talking about the connection to generalization, but there's one more property I want to point out that the evidence has. And it's that it has an information theoretic interpretation. So if you remember that the so the evidence is the, if we define it just to be like the volume of solutions divided by volume of total weight space. This is equal to the probability that you randomly sample a weight vector and it belongs to the solution space. So it's the probability that, you know, you've got a data set, you draw a random neural network. What's the probability that it fits your data? It's probably quite a small probability, but it turns out not to be zero. Sorry, probability that you randomly sample a weight vector and it belongs to the solution space. Then if you ask how many random draws does it take to find a solution by chance? Well, if something happens with probability P, then it takes 1/P draws for that thing to happen on average. So the number of random draws you need to find a solution goes like 1 over the evidence. And if you think about it, if you want to describe to someone a solution, you can tell them the random seed and you can tell them how many draws it took to find it. So the number of bits needed to describe a random solution is roughly like, you know, the number of bits needed to describe the random seed plus log 1 over the evidence. Right, so log 1 over the evidence is just log volume of weight space divided by the volume of solutions. So if there are, the more solutions there are, the fewer bits you need to describe a random one. So at this point, the claim is that it just seems like evidence has a lot of nice properties. has information theoretic interpretation as being the number of bits needed to describe a random solution. It seems that you might intuitively expect that it can measure the hardness of different data sets or measure how good different architectures are. And people noticed this. And there's this quote from David Mackay in 1995 where he says, empirically, the correlation between the evidence and generalization error is often good, but a theoretical connection between the two is not yet established. But he was like a really big proponent of this like class of ideas, even though, right, they hadn't proved everything yet. And basically in the years after 1995, they developed this theory, or like a group of mathematicians, I guess, developed this theory called PAC-Bayes, which is like formalizing the connection between the evidence, which I'm telling you to think of as the volume of solutions divided by the volume of weight space, and generalization. So that's what we're going to look at now. And there's a theorem called PAC-Bayes, but first of all, I'm going to give you the intuition, and then I'm going to like tell you like the theorem statement and how to prove it. So it's like this thing that happened last lecture is going to happen again, but I'm going to like force someone to speak. But so the idea is that we have this situation. I'm going to give you this situation, and you're going to tell me like what your intuition is about what should happen. So we're going to draw a fresh IID train and test set. And then we have a neural network architecture, and it has a weight space. And what you're going to do is you're going to draw a random weight vector W from the weight space. And you're going to run it on the train set and on the test set. And remember, it's being drawn like just from the whole weight space, like maybe using like a Gaussian distribution or using some simple distribution, you know. But right. The first question is, would you expect W to have this random weight vector to have similar train and test error? And like if there's something I haven't specified or something you want to clarify, just like shout out. But does anyone have an answer to this? Right, this process is something that like anyone who's trained a neural network has probably like done a million times. Or like you randomly initialize your network. Does it have like very different train and test error? Or like someone's
the expected difference is 0.
Yeah, so you would expect them to have 0 difference.
But
right.
Jeremy, I think in practice, when people initialize weights, it's always some specific method to initialization. I think it depends on how we define like randomly like a peak of W from the weight space. So usually in practice, we initialize neural network from very small values, right? So I'm wondering if we change the way to randomly select W, will that influence the error?
It shouldn't, right? Like if what you like, basically any way that you can think of to initialize the weight vector that's random and is not like go to PyTorch website and download a pre-trained neural network at random from the list of available networks, but it's something like draw Gaussian weights or like anything you do like that, you shouldn't get different errors on two freshly drawn random samples. Like, you know, like to say that you would somehow, your initialization scheme would somehow need to have like detailed knowledge of what the data samples were.
I have a question about this, Jeremy. So
yes.
like, are there features of functions that would give you larger or smaller variance for this type of discrepancy that you're asking about?
Like I don't, yeah, I don't think so. I mean, like maybe like the idea is that if the training set is like what I'm at, well, yeah, I don't have a good answer to that, but I think maybe people are overthinking this question. It's like, if I make it more concrete, like imagine that you download your favorite data set for like image classification. Let's say it's like CFAR 10, where there's 10 classes. You sample a random weight vector. It's going to have very close to 10% accuracy because there are 10 classes. So a random weight vector is highly likely to be a chance performance, if that makes sense. Like if you're doing binary classification, if you pick a random weight vector on a fresh training set or on a training set, it's going to be at close to 50% performance because that's chance performance. And like it shouldn't, as long as the training set is reasonably large, it should never differ from that.
So to be clear, like there's nothing about particular functions that can throw this off. Like just for any function in some class of functions that you say, this is the same answer.
Yeah, I think so. As long as like, yeah. I think this is just the law of large numbers. It's just like, this doesn't really have anything to do with what the function class is or, but yeah, I realize now that maybe this isn't intuitive. It's like the idea is that because W is not picked with reference to, you've not looked at the training data, you've not looked at the test set and used that to inform which W you chose. You chose a random W. Like the law of large numbers says that like essentially these are two empirical estimates of a mean computed with a large number of samples. So that they're going to both give you quite good estimates of the population mean on typically. Yeah. Okay. Then probably the next part of this is not going to it's not going to go down well. But let me just keep going. So my answer to this is just like yes. Like, because everybody's done that a million times. They drew a random weight vector. Well, sorry, obviously everyone hasn't, but next time you train the machine learning problem, before you actually train it, sample a random model from your model family and run that on the train and test set. And you should get very similar numbers and it should be close to chance performance. But okay, let me just give you the rest of this. It was supposed to be Socratic method, but it's like not worked super well. The next thought experiment is I'm an adversary and I look at the training data and I decide that I'm going to exclude 5% of the weight vectors. So I look at the weight space and I knock out these 5% of weight vectors and I say they're banned, they're not allowed anymore. And then your task is to draw a random weight vector from the 95% of weight vectors that remain. So you draw a random weight vector from the weight space, but you're not allowed to pick the ones that I excluded. Would you expect W prime to have similar train and test error on large, bearing in mind that I used the knowledge of the training data to decide which ones I was going to knock out?
It's pretty clear in this case that's no, because you could choose, you could basically try this adversary, you could try every single possible weight vector and eliminate the weight vectors that have the closest difference between the train and test error. And now what we're left with are weight vectors for which there'd be higher train and test error difference.
Yeah, so it can definitely increase But even if I knock out the 5% that are closest,
I'm guessing that by the overwhelmingly large majority of the weight vectors are like pretty much useless. So that even 5%, you can't really do much to shift. Like there's probably a vanishingly small amount that has a significant difference between training and test error. So I'm
Right.
guessing it'd still be pretty similar.
yeah, it's not even, you don't even really need to appeal to like thinking about the function class. It's like, the point of this part is that the average difference between train and test error, which is like a positive number, let's say we take the absolute difference, the average is small over the whole space. If you have an average being small over a whole space, that means the average has to be somewhat small over like 95% of the space. Because if the average was large over this 95% of the space that excludes these patches, the average would also have to be large over the whole space, because like that's 95% of the space. It's like most of the space.
Jeremy, that also requires observing that the maximum difference is 1.
Yeah, I think it just requires it doesn't require that. It just requires that it's a positive, that the difference is always positive.
If the test error, if the training and test error is allowed to be infinity, then you can completely throw off the expected value by excluding a vanishing small fraction of the space.
Yeah, that would throw it off, but that would improve that would make it the train. If I excluded the ones which had the largest difference,
I see your point. I see your point. Yes. Okay.
So, okay, the intuition which I'm trying to convey, which I failed, admittedly, and that's that's on me. But maybe if you have the time to like look more thoroughly at this, it's like if you have an average that's small over a whole space, it must be small over like, you know, like 95% of the space.
I get that. What you said is so far is like, I get what you said so far. Like if the average is small over the weight space, then if you take 5% off, then still, you know, it's still going to be small. But I feel like I disagree with the fact that the average necessarily over the weight space is small. Like it could, like your expected value could be 0, but the variance could be really extreme.
Well, because it's because we're averaging something like, sorry, the variance could be extreme, but if knowing that the average is small puts a limit on how. Sorry, what's your point about the variance?
I'm saying like
yeah, I think what I'm trying to say is that the average being small, you also know that it's positive, because like we're saying that we're taking the absolute difference between train and test. So if the average is small, it means that most of the values
I see. Okay. If you make it positive, then yeah, I see what you mean.
Yeah, sorry, this would go wrong if it was a sort of signs difference between train and test error.
For this thing, would it be just correct to sort of think of it like in a sort of in the way like you think about entropy with like there's like, I guess I'm like thinking in the case of like where you have like gas and you're trying to say like you have 2 partitions in the tank, but like, and like what's the chance that you'll find all the molecules on 1/2 of the tank, which is just basically nothing. If you have like anything more than like the most rarefied of gases, they're not all going to be spontaneously on one side. Even if you were to start in that very low entropy state where you have like a barrier that you then remove at t=0 and let the gas expand, it's never going to spontaneously go back. Would you say it's something similar where there's like, just because there's so many combinations, there's only a few special weights?
This is connected to entropy, but I'm not 100 like I didn't really want to comment on that now because I'm probably going to say something wrong at this point. But there is like, hopefully this, yeah, let me comment on that a bit later.
Fair enough.
Okay, so my answer here is that yes, because excluding 5% of weight vectors can't change too much.
Yeah, I think one thing maybe that's worth reiterating is that the sampling process is still independent of the training set. So the adversary excludes 5% of the weight vectors, but then you still sample in a way that ignores the training set afterwards.
Yes. So yeah, exactly. So, yeah. If you didn't believe any of this, we're going to go through like the formal or more formal statement, and I'll just sketch how it's proved. So let's do that now. So my like intuitive statement of what we just discussed is that the fewer the weight vectors that are excluded by the training data, the better a random weight vector, sorry, the better a random solution will generalize. So the conceptual jump that we're making here is that we're thinking of the learning process as using the data. So this is the weight space. Remember that given a training set, we said that there were some solutions. What we're now thinking is that we're using the training data to exclude everything except from the solutions. And the mechanism of PAC-Bayes is that if the volume of solutions is large enough, the expected generalization error averaged over the solutions can't be too different from the expected generalization error averaged over the entire space. So this is the mechanism. If there are enough solutions, then on average they will generalize purely because there's enough of them, and this is the entropy part of it, because entropy is entropy measures the number of things. So it can be rephrased in entropy terms or information terms. But the formal-ish statement is so we average over solutions, meaning that we think of this solution space and then we integrate over it. And the thing that we integrate over it is the population error. So remember that the solutions get 100% training error, but they don't get, we're interested in what is that population error. And a simplified version of the PAC-Bayes result says that this is bounded by log 1 over the evidence. And remember that, well, let me expand that in a second. And there's a logarithmic term which is small, and you can basically ignore that. Depends on the number of data points and a failure probability. And then it's divided by the number of data points minus 1. And this result holds for a fraction 1 minus delta of IID training sets. So what this statement is about holding for a fraction 1 minus delta of IID training sets, that says that at the time that you sample your training set, there's a small probability that you get a bad one, which is difficult to learn from. But the idea is that you may think of delta as a small number. So 1 minus delta is large, and this bound holds for most training sets that you would get from random sampling. And delta appears inside a logarithm, so you can basically make this really, really small. And you can just ignore this term, actually. But So now I'm claiming we should just kind of focus on this part of the bound. So the evidence appears, which is good because that's what we've been talking about a lot. And it says that you should actually compare log1 over the evidence to the number of data points. And if log1 over the evidence is much smaller than the number of data points, then the average population error over all solutions is small. So,
Question, Jeremy?
yeah, go ahead.
I think I'm a little bit confused about like the meaning of the left-hand side and also the meaning of evidence here when we have distributions of training sets. Like, is the evidence a random variable now based on the distribution of data?
Yeah, this is how you should think of it. You sample a training set, IID, and with probability delta, everything we're going to say is going to be false. But with probability 1 minus delta, everything we're going to say is going to be true. And what we're going to say is that the evidence is the, it's the evidence for that training set that you just sampled. So this is the evidence for the training set that we sample. And I just wanted to, before discussing it more, also rewrite the evidence in this way that we could think of this as the volume of weight space divided by the volume of solutions. The volume of solutions. And then plus this term that we are just going to ignore, and then divided by the number of data points. So yeah, and then let me explain the left-hand side once more as well. So what you imagine is that we already sampled our training set at this step, and with probability 1 minus delta, everything that I'm about to say will be true. And what the statement is that you go over, for this training set, you look at all of the solutions. There's a whole manifold of solutions, and you go over all the solutions and you integrate their population error, and you average that population error of every single solution. And this average is bounded by something that decays with the number of data points. So if you think about what VC theory said, VC theory sought conditions such that no solution could be capable of overfitting. But this just says, I only care about the average generalization error across all solutions. So it's possible that some solutions overfit as long as most don't. So it's proving something a bit weaker, but it gets a much more interesting result, basically.
So population error is like test error, right?
It's, yeah, think of it as test error on an infinitely large test sample. So it's just like the error on the true data distribution.
And the averaging, is that with like a uniform measure over the solution set, or?
That's something I've kind of glossed over, but it's averaging with respect to the prior measure, which you're actually free to choose, but there's going to be, in any given problem, there's going to be a sort of natural prior, like something like a Gaussian weights or uniform prior, or in neural networks, typically you don't have a better prior than something very simple. Okay. Yeah, at this point, I think I have to keep going because there's not a lot of time, but I'm going to put references to all this stuff. And if you have questions about it after the lecture, feel free to ask me. So the derivation of the result. On homework 4, I've asked you to prove this statement, which says that basically you think of Q as being a distribution with smaller support, and P as being a distribution with larger support. So think of P as being the prior measure over the entire weight space, and Q as being the prior measure but restricted just to the solutions. And this thing that you prove on the homework says averages over the over a more restricted distribution have to be smaller than a measure of difference between the two distributions plus averages over the larger distribution. So this is saying that if the averages can't grow too much if you change from a larger distribution to a smaller distribution, roughly. And there's a beta constant which we can tune. To prove the result, it just involves like many of the steps are just like setting these things to different things. So we set beta to be the number of training points, and this gives us like the thing that we just saw. To give you this like very simplified version, I set P to be the prior on weight space, and I set Q to be the prior restricted to the solutions. And then the KL divergence simplifies to be just log 1 over the prior probability of all solutions, which is just log 1 over the evidence. And then we also set H to measure the generalization error between the training set and the population distribution. The main technical step, which I haven't put in, is like, so these things which I've written here are just like taking this result and setting the different things to particular things that we're going to be interested in. But the main technical step is actually proving this statement, that this average over the prior distribution is small. And this is kind of like the thing that you were saying is not intuitive when I like presented the Socratic thing. But because this is averaging something over a prior which does not depend on the training data, it turns out that this is small. And actually it's possible to prove, but see the references on the website, that log of the average over the prior of e to the m-1 of h of w is bounded with probability 1 minus delta over the training set. It's bounded by log 2m over delta, which is this is something small, so we can ignore this term. That's like the idea of the proof. But I'm just going to move on now. So for the rest of the lecture, I'm going to show you 3 different ways of actually instantiating this idea for neural networks. So what does that mean? So just to show you again, this is the bound, and it depends on this thing that we've called the evidence. And remember that all I want you to have in your head is this picture that we have weight space, we have a solution manifold, which is all the weight vectors that fit our training set. And we're interested in what's the volume of this solution manifold divided by the volume of the entire space. So it's sort of like global properties of a neural network's weight space. Like, how do we access those properties? How can we compute that kind of thing? So I'm going to show you 3 techniques. The first idea is referred to as sharpness and flatness of solutions. So the idea is that you train your network via SGD and you find a particular solution, but you realize that you can perturb the solution in some local vicinity and the properties don't change very much. So you say that the solution has a certain amount of flatness. And we're going to actually do some calculations about this. So, but before we do that, like the thing that's, you can see that something that's wrong with this point of view is that there's not just one solution that you can perturb. The solution space, you could think of it as being comprised of like many of these solutions that can be perturbed. So if you just focus on one of them, right? The claim is already, you can kind of see that you're going to underestimate the evidence because you're going to be ignoring these other patches of solution space. So let's say that there are k solutions. But what we're going to do is we're going to take one of them and sort of think about its flatness, and then whatever we get from that, we're going to multiply by k at the end to account for the fact that there were more solutions. Obviously, k is kind of hard to know, but just like bear with me. So this is where we're actually going to like sort of bring back what does flatness even mean? It's sort of related to the idea of smoothness in optimization. So we're going to like connect back to some of the ideas from the optimization part. So to make some progress, I want you to imagine that we have a neural network that has n neurons, each with a fan-in of d. And moreover, for every neuron, we apply those weight constraints that were on the previous homework. So we constrain every neuron to have the sum of its weight vectors is the sum of its weight vector is 0, and the sum of squares is 1. So we're going to constrain every neuron to lie on a hypersphere. That's what the second constraint says. And and like this is an affine constraint or like a linear constraint, which and the combination of these two constraints says that every neuron lies on a hypersphere of dimension d-2. A d-2 sphere. So if you think about what one solution looks like under this setting, it means that every neuron has a weight vector which points in a particular direction. So this is neuron 1, and its weight vector points on its hypersphere in this direction. This is neuron 2, its weight vector points on this hypersphere in this direction. This is neuron n, the last neuron, and its weight vector points in this direction. And when we say that a solution has a flatness, what we mean is that you can perturb all of the weight vectors and it remains a solution. So if you think about what that looks like, it's saying that there's a sort of cap on this hypersphere, and you can wiggle this weight vector around this cap, and it doesn't induce any misclassification. So these things are called hyperspherical caps. And then let's define flatness to be the largest angle alpha that we can wiggle all the neurons by. Without inducing a misclassification. So this is a way of summarizing flatness of a solution with a single number, which is an angle. Okay, and this is a model. Like there's some issues that you could have with doing this, but I claim it's not the worst model in the world. Okay, so let's compute the volume of a single solution under this picture. And what I hope that you can see is that it's since we have the sort of lots of spheres and lots of caps, and we're interested in like basically what you end up doing is you end up computing how much area does an alpha cap occupy on a single hypersphere, and then you end up multiplying that for all the hyperspheres, and that's like the volume of a single solution. Like, yeah, why? Okay, yeah, I think okay. Like, shout out if there's something that's not clear. So what I've just said is implicitly, what we're doing is we're setting our prior to be the uniform distribution over n hyperspheres. And we're interested in computing the evidence. It's the volume of solutions divided by the volume of weight space. I said that there were k solutions, so the evidence is going to scale with k, and then the volume of each solution is the area of an alpha cap of a d-dimensional hypersphere divided by the total area of that hypersphere raised to the power of the number of neurons. And then there's a result from like from geometry which says that this is greater than or equal to, basically it bounds the term in square brackets as being an alpha cap of a d-dimensional hypersphere is its surface area is divided by the area of the sphere is larger than or equal to alpha, to sine of the angle divided by 2 raised to the power of dimension. So that's saying that in high dimensions, the relative surface area of an alpha cap gets smaller and smaller and smaller as the dimension increases. So under this model, we've like bounded the evidence as this number k, which is the number of solutions which we don't know. And then if we have the fan-in of each neuron, and then we have the number of neurons. And if you remember, the thing that appears in the PAC-Bayes bound is log 1 over the evidence. Remember, like divided by number of data points. So if you plug in what we just did, you get, you basically get, let me just expand this once more. It's k divided by 2 to the n times a sine of d minus 2 n alpha over 2. So log of what, this is the evidence. So log of 1 over the evidence is equal to n log 2 plus n d minus 2 log of 1 over sine alpha over 2 minus log k. And then if the PAC-Bayes bound says we divide this by the number of data points. But the thing that I want to point out is that n times d minus 2 is number of neurons times the fan-in of each neuron, minus 2 because we have 2 constraints. So this is actually the number of degrees of freedom in the network, or n times d is the number of parameters in the network. So we get a generalization bound which compares number of parameters with number of data points. And but the nice thing is that you have this log k being subtracted. So as long as k is exponentially large, meaning that there are an exponentially large number of solutions, then it doesn't matter that you have like way too many parameters because you have this compensating factor. So this is a way that you can, this is a calculation which says that it sort of realizes the fact that PAC-Bayes doesn't care about parameter count. It's not and you can bring a bound into the form that depends on the number of parameters in the network. But it gets this term subtracted. There's a difficulty with, you know, the problem is that we don't really know what k is. But another interpretation of this is that a generalization theory which just relies on sharpness and flatness of a single solution and then neglects this term will lead to a generalization bound that scales with the parameter count, which is not great for neural networks. But okay, so the problem with this argument is that we don't know what k is. So this brings us to the second attempt, which is from a paper which refers to this as breaking symmetries. And the idea is that if you think about what weight space look like, you imagine training your neural net with gradient descent until you find a solution. It has a certain flatness. There's a paper by some people in Toronto, and what they say is, instead of taking the prior to be the entire weight space, we actually started off at a weight initialization, and let's take the prior to be a sort of local ball around the weight initialization that includes the solution. And then instead of computing the evidence as, instead of computing it as the volume of the entire solution manifold divided by the entire weight space, they take it to be evidence is, the volume of that one solution, which is we've illustrated like this, divided by the volume of the ball that is centered on the initialization and covers that solution. So the idea, they call this breaking symmetries because they use a prior which is centered on the initialization and is designed to miss, all these other solutions. So it doesn't matter that you don't know how many solutions there are. There's something weird about this, which is the problem that they have is that they don't know how large to set the prior in advance. So they have like a trick, which is that they basically derive bounds. They derive bounds for like concentric rings of priors of expanding radius, and then they pick the best bounds in hindsight, which is a little odd, and it sounds like you shouldn't be allowed to do that. But the idea is that each bound fails with a certain probability, and as long as they make that probability small enough, then none of the bounds will fail.
I think that's fine. You just choose your delta. If you have like capital L of those, you just choose your delta. You just divide delta by L, and then you apply union bound around all of it.
Exactly. Yeah. But it's a little odd because it's harder to interpret it as a Bayesian prior, because you're saying, well, I don't know what my prior is, so I'm going to have a whole range of different priors, and then afterwards I'm going to find out what the best prior was, and I'm going to use
it's a frequentist upper bound over a collection of Bayesian priors.
Right. So this is just like, if this doesn't make sense, don't worry. But basically, there's something non-Bayesian about PAC-Bayes. Like, it doesn't have to be thought of in purely Bayesian terms. But yeah.
So, I mean, do you think that this is kind of caught up in the problem of like the prior and the training is really driven by the optimization procedure for deep nets? Like, you don't just want any solution. You don't want any minimizer. You want the minimizer that came from your favorite optimizer. Right.
That's a good, yeah. So this actually uses the minimizer that's found by the optimizer. Whereas the thing I'm going to show you, or like how I've presented it, is like, this is good. This is a good generalization property of a random solution drawn randomly from the manifold of solutions. But there's this is like a research question at the moment, but there's a bit of a debate, which is like, some people say, PAC-Bayes says that if you draw a random solution from the manifold of solutions, it should actually generalize quite well, according to this generalization bound. So actually, the optimization algorithm, the role, like, according to these people, the role of the optimization algorithm is just to sample randomly from the manifold of solutions. Whereas there's another camp of people who say, no, the properties of the optimizer are really important. And some people actually think that, some people don't know about PAC-Bayes, and they say that the optimizer is like the most important thing. And it's like, yeah, so that's something which is still getting worked out.
I mean, is there a comment that you have based on your, like, you had a previous lecture about connecting this stuff to GPs?
Yeah, so this is attempt number 3, which is the next slide. So the issue with this technique, well, it actually works, and they actually got non-vacuous generalization bounds, but it doesn't quite match up to how people actually use neural networks in practice. And it also has this, this slightly messy step of, like this concentric circle of priors kind of idea. So the attempt number 3 is by taking the network to be infinitely wide. So the central problem that we were dealing with attempts 1 and 2 is that the structure of the solution manifold in weight space is complicated. We don't really know what it looks like at all. But if we move to function space, it's quite simple actually. So if you remember back to the lecture on Gaussian on the NNGP, so we have this function space representation, which means, we have a training sample and we look at the outputs on the training sample as we vary the weight vector. Okay. So the observation is that for binary classification, the space of solutions in function space is like the set of networks whose outputs have the correct sign, which means that we're interested in actually just an orthant of function space, because these are the networks which have a certain sign pattern. So this is true if we're doing a binary classification problem.
Can you explain the bases here?
Yeah, so what you imagine is that you pick a weight vector in weight space, and for that weight vector, you evaluate the network output across all of the training points. So this is the network output on the first training point. This is the network output on the second training point for that weight vector. So this weight vector might correspond to this point in, it's basically the output space of the network. So if you have n training inputs, then this is an n-dimensional space. And it's just the outputs of the network on your inputs. Okay, but the idea is that we argued that for infinitely wide networks induce a Gaussian measure on function space, so something like this. So in this case, the evidence is equal to the probability that we sample a random vector from a Gaussian with mean 0 and covariance sigma, where sigma is the thing you were dealing with on the homework and depends on the network architecture and the training input. So it's the covariance matrix which corresponds to that infinitely wide network. Well, the evidence is just like, what's the probability that, and I'm visualizing that Gaussian with this ellipse here. And the evidence asks, what's the probability that I draw a random function from my Gaussian process and that it lies in this orthant? So it's the probability that the sign of this Gaussian random vector is equal to y, where y denotes the binary vector of training labels. So the idea is that for binary classifiers, the evidence is equal to an orthant probability under a Gaussian measure, which is like, that's quite a simple geometric object, whereas like in weight space, it was like kind of horrendous. And yeah. So just to summarize, I've kind of shown you three different ways of computing the evidence of a neural network. You know, the first way involved the entire solution space, but the problem was we didn't know how many solutions there were, and we need to know K if we want to get a non-vacuous generalization bound out of this. The second approach like sidesteps the fact that we don't know K by using a different prior that's like close to the weight initialization. And then the third approach goes back and tries to estimate the entire volume of all solutions by taking an infinite width limit and using the correspondence to Gaussian processes. And this is every way that I know of computing the evidence for a neural network. Like there may be others, but there's a fourth way, which is the sort of most naive but impossible way, which is randomly sampling weight vectors and counting how many fit the training data. But the problem with that approach is for any reasonably sized data set, it takes like longer than the age of the universe before you even get one random weight vector that fits the training set. Okay. So like what is any of this useful for, or like why is it just theoretical pondering, or could this actually be used for anything, or in the future is there anything that this could be useful for? And something that like some people are interested in at the moment is using it to do model comparison. So the idea is that you have two neural network architectures. Let's say like one is a CNN and one is an MLP, and you have an image data set. And you find that, you know, you compute the volume of solutions for the CNN and you find that it's larger than it is for the MLP. Well, a Bayesian person would have already told you that that since there's more evidence for this model, then you should choose this model. But they might not have been able to like formalize why that is good advice. And what PAC-Bayes does is it says more evidence implies better generalization of a random classifier, of a random solution. And this, it also connects, PAC-Bayes has moved from the world of posterior distributions to guaranteeing properties of individual solutions. So a random solution is a single classifier. You know, it's not a distribution over classifiers. So that's like one of the nice things, that it actually tells you how things about point estimates in a way. But so does this procedure actually work? And there's a group in Oxford that's been testing this a lot. And I'm going to show you the experiment that I ran on this. So what this is showing you is we want to decide between using a 7-layer multi-layer perceptron or a 2-layer multi-layer perceptron for classifying the MNIST data set. And we're doing binary classification. So we're just saying whether the digit is even or odd. And what this plot it shows you is test error against the size of the training set. And these two curves are the PAC-Bayesian upper bounds on generalization error using the infinite width limit Gaussian process. And these two curves are the empirical result for actually training the networks at finite width. And the green curves are for depth 2, and the purple curves are for depth 7. And the observation is that the ordering of the upper bounds matches the ordering of the empirical result. So it seems that these curves are purely theoretical based on the infinite width kernel of the neural network, whereas these curves are actually like training a neural network. So notice that the bounds are better than chance. So chance is at 50%, and they're better than chance. And also it seems that you can use the bound to predict which architecture is better. Like PAC-Bayesian model comparison seems to work.
But here, the PAC-Bayes bound, that's for randomly sampling weight vectors, right?
Yeah.
So how does that relate to training?
So yeah, that's a great point. So this says that this is a bound on the average generalization error of a random solution. And then this is just the actual generalization error of one solution that was found by SGD, or actually averaged over 3 random seeds. But yeah, they are different things, but it's saying that the empirical performance of SGD, or the optimizer that we used, is, you know, it's not crazily different from the average performance of.
I think a great research question is to relate the distribution of solutions discovered by SGD with random initialization with the distribution over with you know, an uninformed prior over distributions over solutions. Because once you have that, you can completely close this loop in terms of the theory. Oh, sorry.
Right.
Once you have that, and you have a characterization of the breakdown of the approximation of the infinite width limit with a finite width. So there's 2 approximations here. One is infinite versus finite width, and one is the distribution of solutions discovered by SGD with random initialization, and then this uninformed prior distribution over solutions. If you can close those 2, you've completely closed the loop here.
Right. Yeah, something that a critic could say that, you know, this approach is saying this is weight space, here's the solution manifold, and what's the average generalization error over the whole solution manifold. But what if SGD converges to a 0 measure subspace? Like, what if it converges to like this line, which has 0 measure? Then all our results about, do you see what I mean? It has 0 measure, meaning it's a low dimensional subspace. Like it has no volume because it's lower dimensional. Well, then our results on the average generalization error over all solutions don't tell us anything about what happens on that line, because that line doesn't contribute to the average generalization error over all solutions, because, you know, it's low measure, it's 0 measure. So like that's the kind of thing that goes wrong. But in my opinion, it seems to me unlikely that, or SGD shouldn't actually converge to a lower dimensional subspace of the space, because of the fact that you can add noise to the solution and it doesn't break its properties. So you know that you can at least jump off this line a little bit. That's like saying that there's a notion of flatness. But yeah, these are pretty interesting questions, and I think that it's nice that there's this, you can think about these things purely geometrically as well, and then it also relates to like statistical questions. It's like, it's kind of interesting for that reason. Yeah.
The other thing I was going to point out that's interesting about this plot is that you get non-vacuous generalization bounds at only 500 training samples, which I think is surprising for people who study classical generalization theory, who might expect you need like 1 million or 2 million or 10 million examples before you get non-vacuous bounds, if ever.
Right. Yeah. So the number of in the finitely wide networks, the width is 5,000, meaning the number of parameters per layer is like 25 million. But they're still generalizing even with just 500 data points. Even with 100 data points, they're still generalizing. So it's like this notion of parameter counting being important is like is not really true. That comes from classic statistics. And these generalization bounds are for networks with infinite parameters because they're infinitely wide.
So I have a follow-up question on this. Like, what are you using this for? You have to use the data, right? So why not just train? Is this faster to run than training the data at 100, 200, 300, 400, 500?
It's not faster.
So why? I mean, I get that it's interesting, but like, where do you see this going?
Yeah, that's a good question. So, like, the reason I did it is purely because I wanted to understand why, like, how this stuff works. So that's why I did it. But yeah, I think you could. There are things that you can do once you start to. If you like, an example is I saw a talk by someone who, what they say is that you can, once you know that if you believe that the evidence is important, you can do something like you can, if you have a Gaussian process kernel that depends on a parameter, you can actually optimize the evidence with respect to that parameter. So you can actually use it to design the kernel. And you could then, for instance, you could try and map that back to like designing network architectures by like optimizing their equivalent kernel. Like, who knows if that would ever lead to a better network architecture than the one you just get by like trying random stuff, but it's possible. I'm going to suggest that as a project on, I guess, on the next lecture.
I think if I could just chime in briefly, I know we're a little bit over time. I think that, obviously you can make the computation of these bounds computationally faster. I think that's, certainly something that is interesting to work on. And if there's a breakthrough there, then these bounds become much more useful immediately. The second thing I would say is that there will come a point when designing new architectures is going to be this massive trial and error thing. And like having these tools will actually speed up design of architectures, as Jeremy said.
Right. Another motivation I thought about is when, how people say like, our machine learning systems are biased and they're unfair against different groups of people. We actually don't know why, like, how they make their generalizations, even when we want them to generalize. Like, we don't even know, people don't agree on the basic generalization theory, let alone the kind of biases that do you know what I mean? It's like, I feel like resolving this question is actually quite important. Like, just like, why does machine learning generalize? Like, we need to know that in order to like even correct for biases that we don't want our systems to have and that sort of thing. Anyway, okay, so this is the summary. PAC-Bayes relates the expected generalization error of a random solution to the volume of weight space excluded by the training data. The complexity measure is log 1 over the Bayesian evidence for the model class. And it appears to yield generalization bounds that are non-vacuous, can be used to perform model comparison, and can potentially compare the hardness of different data sets. And next lecture, we'll discuss project ideas.